definition of generalized degree of freedom is the limit of the capacity per user normalized by log SNR. As you take limit SNR goes to infinity, it's fixed log INR over log SNR. Okay, so this is just, you can think of this as a normalized capacity, because the log SNR is approximately log 1 plus SNR, which is the interference capacity in the point-to-point channel. Okay, so basically I normalize the capacity per user in this interference channel by the interference-free capacity. Okay, so now I'm going to jump. So this is the curve of that limiting performance, and this is going to be our baseline for comparison. So again, I'm plotting the generalized degrees of freedom versus log INR over log SNR. So you can think of log INR over log SNR as just the ratio of the interference and the signal power in dB scale.
So each one of these points is a limit point. Each one of these points is a limit point.
Which point?
On this graph. Right?
On this graph, this is the each point on this plot is the limit.
When you take the SNR.
Yes, with a fixed log INR over log SNR. Okay.
Why did we have this jig-jaggedy line in it? We
Okay.
talked about that once.
Yes, yes. I can show you later on these bubble models. Later.
Okay.
Yes.
And that was, okay, we have different regimes of operation.
Yeah, that's right. Because basically it's because that you have a tension between the interference and the your desired signals, and they are operating in a particular fashion in the receiver signal space, and this is going to cause you this kind of zigzag behavior. Okay, so now with cooperation, I can define a similar notion of generalized degrees of freedom. Again, I'm going to take the limit of capacity per user normalized by log SNR. But now we have one additional parameter, which is the cooperation rate, CB. Okay? And because I want to study the cooperation limited behavior, so I'm going to take the limit in addition that I'm going to fix the ratio of CB over log SNR. Again, I'm just taking the normalized because I'm normalized by the interference-free capacity. Okay, so now here are some numerical results. Here's the plots for CB over log SNR equals 1/6, 1/3, and 1/2. Okay, so let's look at the weak interference regime, where log INR over log SNR is smaller than equal to 1, smaller than 1. So I'm going to look at these two calculated points, where log INR over log SNR equals 1/2 and 2/3. To illustrate that the gain from receiver cooperation is different at these two different regimes. Okay, you can see from this plot that the gain from receiver cooperation is different. So first, at this point where log INR over log SNR equals 1/2, I'm going to plot again our performance measure, which is the generalized degrees of freedom, versus the capacity at the cooperation limit, CB over log SNR. So from this plot, you can see that until saturation, the slope equals 1, which implies that one cooperation bit buys one more bit for the users. Okay, so if you invest one more bit in the backhaul, you can get one more bit for the users at this regime, where INR is 1/2 of SNR in dB scale. For example, 20 dB versus 10 dB.
But where I don't see the 1 here, I see 1/2. No, I actually see 2.
No, on the y-axis, the base is 1/2. It's 1/2. So the slope is 1. Okay. Okay. So in order to explain why, I want to look at this point where CB over log SNR equals 1/4. Furthermore, I want to use a linear determinist channel. So because the Gaussian channel is complicated because you have this additive Gaussian noise, and also the interference is coming to play. So it's hard to study the interaction among the signals and the interference. So these people, they propose this linear model, which is a good approximation for the Gaussian channels in many scenarios. In many scenarios, like the relay channels, relay networks, and in particular in these two user interference channels, also a good approximation. So I'm going to use this model to convey the key ideas. Why we have one corruption bit bias one bit. Okay? And the corresponding model is here. So in this LDC model, each circle represents one binary bit. And whenever you have two incoming links at the receivers, so the left-hand side is the transmitters, and the right-hand side are the receivers. Okay? And whenever there are two incoming links at the receiver bubble, I use a binary addition to sum up these two bits. Okay? And in the corresponding Gaussian channel, each circle corresponds to 1/4 log S and R in this example. Okay? So you can see that this is, you can think of the bubbles are the binary expansions of the transmitted and the received signals. So when there is no cooperation, what's the optimal strategy for these two-user linear deterministic interference channel? It's just to turn on these bits that does not cause interference at the other receivers. Okay, so greedy algorithm would be to turn on these bits that does not cause interference at all at the other receiver. Okay, and once you turn on these bits, you can see that you cannot turn on more bits on the upper levels because it will cause collisions at the other receiver. Okay, so now I can achieve 2 bits per user, but the interference-free capacity per user is 4 bits because I have 4 levels in these direct links. So I achieve the general distribution freedom of 1/2, which is the black dot. And now I want to achieve the dot on the blue curve, which is 3/4. So I want to achieve 1 more bit for each user. So I turn on this A2 and B2 bit. Okay? Now notice that when I turn on this A2 bit, I will cause collision here at the LSB at receiver 2. Okay? So but I'm not causing collisions at receiver 1, right? Because the level is not occupied there. Okay? So in principle, I will need 1 corruption bit to get rid of this interference, to get rid of this collision. And when we turn on this B2 bit, I will also have a collision at receiver 1, but not at receiver 2. So in total, I have 2 collisions when I turn on these 2 more bits for the users. Okay? I can use 2 corruption bits in total to get rid of these 2 bits easily by sending A2 bit to receiver 2 and B2 bit to receiver 1. Okay? So I achieve this point where now I have 3 bits per user, and the interference-free capacity is still 4 bits. So the generalized usability is 3/4. So I have this, in this particular point, I have 1 corruption bit by 1 more bit. And the reason is very simple. It's because that when I squeeze 1 more bit into the system, it will cause collision at 1 receiver, but not at the other guy, but not at the original receiver. So you will, in principle, need 1 corruption bit to get rid of this interference, get rid of this collision.
This is a deterministic model.
Yes.
Okay.
By someone and David.
When you say saturation, you're talking about referring to the Treacher's diagram in the economic region and the differences.
Yes. So basically,
right. So that's
So previously I had this curve, right? This is achievable rates, and I said that I break down here, and this is the upper bound. I break down here because this is a linear region, and this is the saturation